Bob Wells here, and welcome to another episode of the Undercurrent Stories podcast. Have you ever looked up at the night sky into space and wondered what it is? What about time? Where did the universe come from, and what about black holes? Well, here to talk about black holes and answer some of those questions, I'm joined by Marcus Chown. Marcus is an award-winning writer and broadcaster, formerly a radio astronomer at the California Institute of Technology in Pasadena. He is a Royal Literary Fund Fellow at Brunel University. His books include The Ascent of Gravity, which was the Sunday Times Science Book of the Year, and he just brought out his latest book, which I've just read, which is fantastic, A Crack in Everything, How Black Holes Came in from the Cold and Took Centre Cosmic Stage. As well as writing, Marcus was a regular guest on the BBC 4 comedy science show, It's Only a Theory, and he often appears on Channel 4's Sunday Brunch. He has appeared at a variety of events, from the Cheltenham Literary Festival to the Sydney Writers' Festival, from the National Theatre to the Wilderness Festival, and he has done stand-up comedy at a variety of venues, from an upturned inflatable cow on London's South Bank to a glass-bottomed boat in a shark tank at the Brighton Sea Life Centre. Hello and welcome to Undercurrent Stories, Marcus.
Hello, Bob. That was a fantastic introduction. Thank you.
Well, thank you. But I said, hey, I'm sorry I broke up in laughter a little bit. It made me giggle. The glass-bottomed boat in a shark tank doing comedy. That must have been interesting.
It was a weird thing because, it was weird. There were a number of people doing stand-up and we were on this platform and we were put in the middle of this shark tank. So, of course, you had to wait your turn. And when you went to the microphone, you had to be very careful that you didn't tip this little boat over, with your weight. So someone had to move to the other side to counterbalance it. And of course, you really had to make sure that you'd been to the loo before, because you had to wait about half an hour. And we saw these sharks circling beneath us. It was peculiar.
Yes.
But the most peculiar thing is they never paid me. And I was unable to get the money out of them. So, it wasn't actually the Brighton Sea Life Centre, but it just shows you it's difficult sometimes to get actually paid for what you do. Not that I'm bitter.
Yes. No, not at all. Not at all. No, I know exactly what you mean, because I play in a band and sometimes it can take a bit of time to get a performance fee.
Yeah.
Whereas if you're doing the catering, you probably ask for the money up front and you get it. So there's probably a story, a bit of a lesson there. Yeah. Anyway, before we talk about your life as a writer and a broadcaster, please, can you just tell us a bit about yourself and your life's journey and how you came to write a book about black holes?
Well, I mean, this is a weird thing because my mum and dad left school when they were 15. They didn't have any qualifications. They'd grown up during the Second World War. Their schooling had been interrupted by the Blitz. And yet, for some reason, when I was about 8, my dad bought me a book on astronomy. It was called Dr. H.C. King's Book of Astronomy. He was the director of the London Planetarium. And it kind of grabbed just sparked my interest. My dad bought me a very small telescope. I used to poke it out of the upstairs window of our flat in Finchley in North London, and I would see the moons of Jupiter above the orange glow of the North Circular Road. I could just about see Saturn's rings. And then, of course, I was unbelievably fortunate to be a child when the first human being stepped on another world, Neil Armstrong, in 1969. And I don't know, why are some people, why I'd like to know. Unfortunately, my dad died. I never asked him why he encouraged my interest in astronomy. Was there someone when he was growing up who got him interested? I just don't know. It's too late to ask now.
I mean, you're a very similar age to me. Looking at it, almost identical. And we are now, aren't we? And growing up in the 1960s with the space race, it was quite a sort of dynamic decade, really, wasn't it? From when Kennedy said, right, we're going to get a man on the moon. And, a few years later, we got somebody on the moon. So I remember watching the moon landings, which were quite incredible.
Well, I do as well. And I just think, my God, how long has the Homo sapiens been around? I don't know, a million years or something like that. And to just be alive at that moment when a human being steps on another world, which is, as significant a moment as the moment the first, fish got stranded on dry land, Um,
Yeah.
Absolutely incredible. And it was a time of enormous optimism. And I do remember collecting all these cards, coloured picture cards, which came out of, I think, Typhoon Tea. And there was, there was one which was showing us landing on Mars in 1980. And there was complete confidence that we would be landing on Mars in 1980. And that all went by the way. And I don't remember much pessimism about the environment or anything like that. Of course, global warming was going on all the time, and had been recognised since about 1850 that this was happening. But we didn't get any of that bad news. We only got the optimistic news.
Yes, it was interesting, wasn't it? We had supersonic flight with Concorde at the turn of the 70s, late 60s. We had man on the moon. And I think the general assumption, certainly my assumption, was that things would just carry on evolving. And yet they didn't. They've evolved in different ways, but not in terms of, passenger flight or space travel, really.
But if you go back and if you look to, for instance, the Western colonization of North America, then you see that Columbus arrived in the West Indies. What was it, 1498? And there really wasn't a concerted attempt to colonize until the 1600s. So there was a really big gap, more than 100 years. And so maybe we were unrealistic, thinking that someone would step on the moon and then there'd be cities on the moon and all this kind of stuff within years. Maybe we were just too optimistic.
Yes. So your interest in astronomy, as you mentioned, sort of started as a child. When did you decide to make it a career?
Well, I liked science at school. I didn't realise that astronomy was really science. It was never taught, but then I don't know. In my teens, I realised there was a topic known as astrophysics, and I thought, oh, that's what I want to do, And my dad was very good because he encouraged me to do anything that I wanted to do. Fortunately, he had this ridiculous faith in me, and I think it was a faith that he had because when he'd done national service, he'd mixed with people who'd been to Cambridge. He was in the Royal Signals, and he'd realised that he was not stupid. He just hadn't had the opportunities that they had had. But his son and daughter, I mean, my sister, would have. So I think he had this amazing faith because he knew what he could have done had things been different. And he always encouraged me to do what I wanted to do. I mean, you wouldn't really, generally you'd say do something that's going to lead to a useful job, not astrophysics. But actually, it has led to a job. So he was actually right. And one of the things I really liked at school as well was English. I really liked writing essays. And unfortunately, at A-level, it was not possible to do arts and science A-levels, which is ridiculous, really. So I went to university, did physics, eventually went to Caltech in California, where I did radio astronomy. But by which time I'd kind of thought, really, I need to get back to writing. That's what I really like doing. And I wrote to newspapers and things back in England, and they all wrote to me telling me to get lost, including New Scientist that eventually gave me a job. so my lesson I learned was that persistence is the key. Keep persisting,
Yes.
And if you can stand lots of rejection, and I can't even begin to tell you how much rejection I've had. I mean, certainly even with books now, you get rejected so many times. The key is to be persistent, really.
We were talking before we went on air that the book that you sent me about black holes, I read on holiday, which some might say is that a right type of book to read on holiday? But I have to say it was. Holidays always give you an opportunity to, spend a bit of time in one sort of silo almost, and I got really into it. But what I liked about the book, two things really. One was it was relatively easy to understand. You didn't have to be an academic or a scientist to understand it, certainly in my case. And also how you combine the science and the hard facts, which go into, you go into a lot of detail, micro and macro, with the narrative of the people over the last 100 years plus who have been involved in discoveries and stuff like that. And what sort of struck me was that everybody who you either interviewed or you read about and did your research, there's an amazing story behind all these. They're real people. And one particular one was the Indian scientist, and Subramanian Chandrasekhar. I think that's the way you pronounce it.
Subramanian Chandrasekhar.
Thank you.
Yeah.
Yeah, I did try. I went on to Google earlier on and looked at a pronunciation, but Obviously not particularly good.
Well, I hope I've got it correct.
Thank you. What I found was that he was almost sort of disregarded and poo-pooed almost as a young upstart, and yet and it was great because at the end of the day he did have something to say and was recognised later in life. Could you just tell the story about him, please?
Yeah, well, he was coming to England on a ship from Bombay in 1930. He was 19 years old, and as the ship was going through the Suez Canal, he sat on deck in a deck chair, and he basically applied the newfangled quantum theory, which was the theory of the microscopic world of atoms, to stars, to dying stars. And it had been, I mean, in 1915, 16, Carl Schwarzschild had discovered that Einstein's theory of gravity predicted the existence of black holes. So basically, at the end of a star's life, it ran out of fuel. It would shrink down to what we call a singularity, where everything skyrockets to infinity. So that's a ridiculous situation. So everyone, including Einstein, thought there must be some other force that opposes this collapse. And then quantum theory came along in the 1920s, and it looked as if there was such a force, because there's a thing called the Pauli exclusion principle, which basically says that electrons cannot sit on top of each other. And this is why tables are solid. This is why the floor under your feet is solid. And this is why matter has some extent and doesn't collapse down to a point. So this is it kind of provides an aversion that electrons have to being pushed together. So as a star runs out of fuel and gravity takes over and shrinks it because there's no heat pushing back outwards, eventually the electrons and their aversion to each other stops the collapse. And you get something called a white dwarf, which is a star about the size of the Earth, but which weighs as much as the Sun. So every cubic centimetre weighs probably as much as a family car, a very dense object. But Chandrasekhar realised that people had forgotten one detail, and the detail was Einstein's theory of relativity, because it basically says nothing can travel faster than the speed of light. So if you imagine as the star shrinks and electrons are pushed closer and closer together, but they kind of really react to that. They try and repel each other. And when you squeeze something, they get faster and faster, because when you squeeze something, it gets hot. Heat is microscopic motion. They get faster and faster. And it's this kind of drumming that they kind of drum like raindrops on a rooftop. That's the kind of force that's pushing backwards. And of course, Chandrasekhar realised they can't drum faster than the speed of light. So they're kind of sapped of the ability to push back. And it turns out that if a star is more than about 1.5 times the mass of the Sun, it cannot form a white dwarf. The collapse continues. So the aversion of electrons to each other, this outward pressure, cannot stop the collapse. And the collapse continues onwards. So basically, he'd shown that a black hole was unavoidable. And when he arrived at Cambridge, he was very much a fish out of water. He didn't speak the language very well. He was very lonely. And the big figures at Cambridge, he was intimidated by them. And in particular, his hero was Arthur Eddington. Arthur Eddington was probably the most important astronomer of his day. He proved Einstein right by finding the bending of starlight during a total eclipse, and had made Einstein the kind of superstar we know today. And Eddington was very, very bad to Chandrasekhar, did not believe that in his work. And it was in fact, humiliated Chandrasekhar at a meeting of the Royal Astronomical Society in about, I think, 1932. Absolutely humiliated him, to the extent that Chandrasekhar moved into other fields. He thought, well, I can't really continue with this work. I've got to move to another area of astronomy because this great figure, Arthur Eddington, thinks I'm wrong. And of course, the irony is that, in fact, Eddington died in the 1940s. And eventually, I think it was about 1983, Chandrasekhar got the Nobel Prize. So he actually got his vindication. But he spent his whole life really carried this burden of feeling that he was not adequate, that he had failed. But then he got this vindication in the end. That was a long story.
Well, yeah, I mean, there's a really good chapter dedicated to it, and it's a great ending, I think. And there's many more of those sorts of stories in the book about the various people that got involved, and stories of cooperation, scientific jealousy, and all the rest of it. It's
Yeah, I
quite
mean,
interesting.
scientists are human beings. They really are.
Yeah, yeah. What I find interesting, well, in fact, almost not skeptical, but I do question is this sort of, you've got the theoretical mathematics on one side, and yet it's sort of telling you what is up there in the universe and in space, which I find quite hard to grapple with, because do we really know it's there?
I mean, that's absolutely incredible, because that is exactly the thing that amazes me. And in fact, one of the previous books was called The Magician, but they changed its name to a breakthrough in the paperback, because it had been published on the verge of the first lockdown, COVID lockdown. So I wasn't able to do any publicity. So the book didn't do very well. And then the publisher thought, well, we'll change the name, which of course confuses people. And eventually, you get people that buy the book twice and get really annoyed. But anyway, but that was exactly what I was interested in. I thought the book was called The Magician, because the central magic of science is this idea that you can write down on a piece of paper, on a blackboard, on a whiteboard, a mathematical formula that predicts the existence of something. And when you go out and look for it, you actually find it. So, for instance, I mean, a good example might be in 1964, Peter Higgs was on a camping trip in Scotland. He'd gone to the wettest place in Scotland for his camping trip. In fact, he'd made a mistake. Someone had recommended it, telling it was the driest place in Scotland, but they'd made a mistake. And during this trip, he did think, he thought of, he realised that things get in the universe get their mass because of the presence of this ubiquitous Higgs field. Right, we're in it. We're like goldfish. Goldfish probably not aware that they're actually swimming in water, because it's everywhere around, and we're not really aware that we're in air because it's all around us. But the Higgs field is all around us, and we weren't aware of it. And he predicted its existence, and it's the interaction of electrons and protons and things with this Higgs field that gives them mass. And 40 years later, so he predicts this, 40 years later, at a cost of 5 billion euros at the Large Hadron Collider in CERN near Geneva, there it is, the Higgs particle. And this happens time and time again. I mean, Paul Dirac, the great, almost, I think it was an autistic physicist, quantum theorist in the 1930, he tried to describe an electron moving near the speed of light with a formula we now call a Dirac equation. It's one of two equations inscribed on the flagstones in Westminster Abbey. And when he wrote this equation down, he realized that the machinery of the equation was duplicated. It didn't just describe an electron, it described a positively charged electrons. Electrons are negatively charged. And of course, this was the first particle of antimatter. So it is quite astonishing. So to put it in a nutshell, there appear to be two universes. There's the mathematical universe, which you can write down on a piece of paper, and there's the real universe. So there are these two twin universes. And of course, the question, why is mathematics able to do this? Why is mathematics so good at describing a universe? Is an unanswered question. So, and it is to me the central magic of science. So much so that scientists find it unbelievably difficult to believe, and often they don't believe the predictions of their own mathematical theories. So their problem is that they take their theories too seriously, but they don't take them seriously enough. So there's countless examples of the case of Dirac. He didn't realize that was predicting a universe of antimatter. He thought there was something wrong with his equation. So yeah, you put your finger on something really, really amazing. The central magic of science. And we don't know that there was a paper written by the Austrian physicist, Eugene Wigner, in about 1960. It was called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And Dirac himself said, God is a mathematician of a very high order.
Hi, it's Bob here. Just a quick interlude. Hope you're enjoying this episode. And if you would like to hear more interesting interviews, we have over 80 episodes to date with many fascinating guests talking about a wide variety of topics which include music, history, philosophy, fitness, food and drink, adventure, contemporary culture, and many, many more. I'm sure there's something that you'd really enjoy. So all you need to do is just visit undercurrentstories.com or search Undercurrent Stories in any of the podcast platforms. And now back to the show. That's interesting. Now, I'd like to just go back to black holes, if I may, because you went into it with a bit of detail, but put simply in a couple of sentences, if you can, because we've all got our own ideas. What is a black hole?
A black hole is simply a region of space where gravity is so strong that nothing, not even light, can escape. So it's basically black, cut off from the universe. Obviously, a better picture was given by Einstein. Einstein, in 1915, he came up with a new theory of gravity that supplanted Newton's, and it really showed that gravity is, in fact, the curvature of space. Okay, so the Earth goes around the sun because the mass of the sun creates a kind of valley in space-time, and the Earth goes around the upper reaches of this valley, rather like a roulette ball in a roulette wheel. Now, you may think, of course, we can't see it because it's a curvature of four-dimensional space-time. That's why it took a genius like Einstein to notice. So in this picture, then a black hole is simply a bottomless well from which light cannot climb out. So it's pretty much the same picture. So it's cut off from the rest of the universe.
And how many in our own solar system or our own galaxy? How many black holes have we got?
The estimate is about 100 million. So these things are remarkably common.
100 million black holes?
Yeah, we've only seen 50 in our galaxy. They are stellar black holes are quite difficult to spot. But basically, the interest in these objects was stymied for a long period of time. Even great people like Robert Oppenheimer, who was the father of the atomic bomb, he investigated black holes in the 1930s, but he made the mistake that everyone made. He thought that black holes would be black and small. Well, how do you see something that's black and small against the black of space? But the mistake he made was that stars tend not to be on their own. In fact, the sun is quite unusual in being a solitary star. Most stars are binaries, a pair of stars, maybe three, maybe four. And having a companion makes all the difference. Because if a black hole has a companion, it can suck material off its companion, which will swirl down like water down a plug hole onto the black hole. And as it does so, it creates what we call an accretion disk, which can be heated to millions of degrees and give out very bright X-rays, which we can pick up on Earth. So this is the means by which we see them. So the mistake Oppenheimer made is he forgot that black holes are actually always embedded in an environment, and that makes all the difference. So unbelievably, the black holes we found in the universe are some of the most luminous objects in the whole of the universe.
Oh, so they're not black?
Absolutely not black. I mean, some of the brightest objects. I always say, I just did a talk this weekend about it, and the term black hole was coined in 1967 by John Wheeler, who was an American physicist. He was actually the supervisor of a famous physicist called Richard Feynman, who I was fortunate enough to be taught by when I was a student at Caltech. And this was, in many ways, it's a very good term, black hole. It paints such a good picture, such a vivid image in people's minds that we use it in everyday language. I've lost my passport down a black hole. I've lost this. Yeah. It's reused by everyone. But in many ways, it paints completely the wrong picture, because the black holes we've seen are neither black nor holes. The ones that we've seen include some of the brightest, most luminous objects in the universe. That's why one of the chapters of my book is called The Unbelievable Whiteness of Black Holes. And the other thing is that they are, yes, we do see evidence of material falling in, but the predominant thing that we see is actually material coming out. And very often we see these amazing jets coming out from the north and south poles of supermassive black holes, these giant black holes in the center of galaxies, and they can extend for millions of light years across space. So the term black hole, unfortunately, it's a brilliant image, but in many ways it paints the wrong picture.
Right, being very practical about this, I'm up in space in my spacecraft.
Yep.
How near a black hole can I get without getting sucked down it?
Well, how near can you get? That's a very good question. There is what we call an event horizon around a black hole, and that is basically at the point of no return for infalling matter and light. So this is kind of, in a way, gives you the extent of the black hole. In a way, the black hole is nothing. I mean, Chandrasekhar, who we were talking about earlier, mentioned or said that the black holes are actually the simplest objects in the whole of the universe. They are fabricated of nothing other than space and time. So the star, the matter that formed the black hole, it shrank, and as far as we know, shrunk down to a point and disappeared. But it left behind this kind of bottomless well in space time. But we so it doesn't really have a surface, but we define the surface as the event horizon, and it's kind of a membrane around the point of no return. So if you go through the event horizon, you can't get back out again. So if the sun were, for instance, a black hole, which it couldn't really be, but if you could squeeze it to make it a black hole, it would be 6 kilometers across, and so if you got within 3 kilometers of the center, you couldn't come out again. And of course, when they spin, most black holes spin, and just like the Earth, it bulges at the equator, because of centrifugal force, and so the actual it's not necessarily a spherical surface, the event horizon. It's more like an oblate spheroid.
I was very interested to see a photo of a black hole. And I mentioned earlier on that a lot of cooperation exists between scientists, and it was only relatively, was it about 2021 or 2 that a photo was actually produced of a black hole? Could you just tell listeners how that was achieved?
Yeah. I mean, the basic problem, we're talking about radio astronomy here, because the thing about radio waves is they do penetrate the gas. I mean, when you look at the night sky, the center of the galaxy is about 28,000 light years away. But you can probably only see about 1,000 light years, all the stars you're seeing within 1,000 light years. And the reason for that is this dust hanging in interstellar space. It forms like a curtain. So starlight it's very hard for starlight, visible light, to come from the center of the galaxy. It just gets absorbed by all this dust. But radio waves do penetrate, so they actually give you the option. The big disadvantage of radio waves is their wavelength is 1 million times greater than that of visible light, which means when you use a radio telescope, your vision is 1 million times blurrier than it would be with an optical telescope of the same size. So you think, well, you can actually compensate for this, because the bigger the telescope, the bigger the collecting area, the finer the detail you can see. But then you're stuck, because if you build a radio telescope more than 100 meters across, it collapses under its own weight. So the solution that astronomers have come to is basically have a whole load of radio telescopes connected in some way. They could be connected by cables, or they could be on other continents. And this is what we call very long baseline interferometry. And the image you're talking about was taken by such an array called the Event Horizon Telescope. And at the time the first image was taken, which was published, was 2019. The second image, you're right, was 2022. There were about 8 dishes. So they all look at the same, in the same direction. They all looked at where they thought there was a black hole. And they record what they see, which is, the intensity of the radio waves. And then those recordings are flown together to supercomputers in 2 places. One's in Haystack, Massachusetts. The other one's in Bonn, in Germany. And on a computer, they are combined so that we effectively get an image that you would have got had you had a telescope the size of the Earth. So that would show you very, very fine detail. But of course, it's a terrible, terrible telescope. So imagine you're looking at the Earth, and there are specks. There's 8 specks where these 8 dishes are. Imagine if this was an optical telescope. So we have a mirror, a silvered mirror, and we black it all out except for 8 tiny little black specks. You'd imagine you'd get a really bad image, wouldn't you? Because most of the mirror would be actually blotted out. So that's exactly what it is. So it's a very crude image, but it did enable them to image a black hole, a supermassive black hole. Now, we've discovered, we don't even know why, but every single galaxy, there's 2 trillion in the universe. We live in the Milky Way. Every single one has a supermassive black hole in its heart. So this is not a black hole of a few times the mass of the sun. It could be billions or even tens of billions of times the mass of the sun. We absolutely don't know how they got there and what they're doing there, so it's a big mystery. But it turns out that there is a one in a nearby galaxy called M87, which was imaged in 2019. This is a 5 billion, 6 billion times, 5 billion times the mass of the sun. It's an enormous black hole. And then we imaged it took 3 years later, an image of the one in the center of our galaxy, which is called Sagittarius A star. Coincidentally, that was discovered exactly 50 years this year. So, and we were able to get an image there. Now, the amazing thing is that the one in the center of the galaxy is 1,000 times smaller than the one in M87, but it's 1,000 times closer. So the two images look roughly the same. They have the same apparent size.
I see.
And the reason it took so long to get the image of our one is because it's 1,000 times smaller. It rotates 1,000 times. The disturbances are likely to happen 1,000 times more. So if you imagine, if you were to photograph a very elderly Labrador sleeping on the lawn, it'd be really easy. That's M87. Okay, but now imagine a very, very boisterous puppy bouncing around your garden. That'd be much more difficult. That's why it took an extra 3 years to actually to get the image of the much more active, there's much more motion, much more disturbance in the supermassive black hole at the centre of our galaxy. But what's so fantastic about this is that the two images, I'll just describe them. They both show a black void, and around it, a glow. I mean, the scientists used an orange glow, but of course they were picking up radio waves which don't have those colours. But basically, you're seeing hot gas around the central black hole about to be swallowed by this void. And when it disappears over the edge of the void, which we can see in these images, it's rather like water going over a waterfall. And that material is never seen again in our universe. It's basically gone forever. So that's incredible. And inside a black hole, we think that space and time itself come apart. They fragment into something more basic. We don't even know what it is because we don't have a theory to describe it. So inside we see the end of space and time. So I often say at the end of my talks, as human beings, we tend to beat ourselves up for global warming and pollution and all the terrible things we've done. But sometimes I think we need to pat ourselves on the back and think, wow, we're jumped up 8. We came down from the trees onto an African savanna 1 million years ago. We've got a brain which is at 1.5 kilograms of mostly jelly and water, but we've seen to the very edge of space and time. So I think that's pretty amazing.
Yeah, and over the last 100 years, when you think what's actually taken place through mathematics and proof of it, and then you look ahead in 100 years' time with more powerful computers, technology advancing all the time. What will we know in 100 years' time? It's quite fascinating.
It's extraordinary. I mean, Sagan remarked on how lucky we were. I mean, he died probably 20 years ago now, but Carl Sagan remarked on how unbelievably lucky we were, because we know the extent of the universe. We can see to its very edge. We know its content. We can count up there are 2 trillion galaxies like our Milky Way. We have a pretty good idea where it came from. We think it burst into existence 13.8 billion years ago in a fireball, which we call the Big Bang. It expanded, and cooled. Out of all this debris, they congealed the galaxies that we see around us. This is a picture that previous generations would have killed for. We don't have to speculate that the universe is sitting on the back of a turtle. We actually know where it came from and its extent. And not only that, but we have a really good chance of answering really fundamental questions within the next 10 or 20 years. What is the universe? Where did it come from? What drove the Big Bang? What is space? What is time? These are kind of questions that they were the preserve of religion, but we have a good chance of answering. And so I think we're unbelievably lucky to be alive today.
Yeah, I mean, some of those questions. I mean, I've got an obvious one now. I mean, this is what there must be some scientists working on the fact that there's an estimated 2,000 galaxies in the universe.
2 trillion.
How do we know where the extent? Oh, sorry, 2 trillion galaxies in our universe. What's beyond our universe?
Well, as far as we know, more of the universe. Okay, so the universe is surrounded by a light horizon. Okay, so it's because the universe was born. Okay, so the universe hasn't existed forever. It was born about, say, let's say 14 billion years ago. That means we can only see the objects whose light has taken less than 14 billion years to get here. Objects whose light would take 15 billion years to get here, well, its light hasn't arrived yet. So that means that everything whose light has taken less than 14 billion years is imagine it's, in this giant soap bubble, okay? 2 trillion galaxies.
Yeah.
We're in this bubble. The light has had time to get here. Beyond the edge of the bubble, what we call the horizon, there are galaxies whose light hasn't got here yet. So it's right. It's exactly like the. So we talk within this bubble. We call it the observable universe. Okay, that's because that's all we can observe. But we think there's more beyond the edge. So the horizon, this membrane around the universe, it's rather like the horizon at sea. I mean, you look out, you know there's more of the sea beyond the horizon. We know there's more of the universe beyond the horizon. I mean, it's quite possible that the universe is actually infinite in extent, but actually we can only see a small bubble of it. And every year, more stuff comes over the horizon because the universe becomes slightly older. But,
We can only see, was it 15.8 billion light years away?
Well, actually, we can see further than that because it turns out, although the universe is 13.8 billion years old, we can actually see 42 billion light years away. And that's because the universe expanded far faster than light in its first split second of existence, which you might think is impossible, but that's what actually happened. But one proviso. In 1998, we discovered something which was probably one of the most unexpected discoveries in the history of science. So we know that the universe is expanding. We can see all the galaxies flying apart from us, just like pieces of shrapnel, And if we run that expansion backwards like a movie in reverse, that's why we get to this time, 13.82 billion years ago, when all the galaxies were stuck together, in the Big Bang. And we really thought that the only force operating was gravity, like an invisible elastic web connecting all the galaxies, So gravity would be slowing down that expansion. So the expectation was it was slow and slow, and then we discovered that it was actually speeding up. Which was contrary to all expectations. And we've had to postulate the existence of stuff called dark energy. And it accounts for 2/3 of the mass energy of the universe. It's invisible. It fills all of space. It's no doubt in the room where you are and where I am as well. And it's got repulsive gravity. And its repulsive gravity is speeding up the expansion of the universe. Now, what this means is, what it actually means is that I told you that more of the universe will come over the horizon every year. We'll see more of the universe. But because of this accelerated expansion, the opposite will actually happen. And the horizon will eventually begin to shrink down and down and down until in about 100 billion years' time, the universe is about 10 times the current age of the universe. The horizon will shrink down until the Milky Way, where we live, is the entire universe. So there'll just be one galaxy in the universe, and we won't be able to see beyond that. What about
that? It is literally mind blowing, Mark.
But we don't know.
It really is.
But we know that dark energy switched on. We don't. By the way, we've got no idea what dark energy is. I mean, when we use quantum theory, our very best theory of physics, which basically predicts what we observe in laboratories to 10, 15 decimal places. It's the most successful physical theory ever devised. When we use it to predict the energy of the vacuum, the empty space, which is the dark energy, we get a number which is 1 followed by 120 zeros bigger than what we observe. That's the biggest discrepancy between a prediction and an observation in the history of science. So it's telling us there's something desperately, desperately wrong with our picture. So we see that this dark energy switched on. So the universe its expansion was slowing down until about 10 billion years ago, and it began speeding up again. And because we don't know what switched on this dark energy, because we don't even know what it is, it could easily switch off again because we literally know nothing about it. I mean, we are in a shocking position in science. I don't think most scientists recognize where we are. We've discovered, after 350 years, that we've only been studying 5% of the universe. Only 5% is made of atoms and all the kind of things that we see around us. 95% is entirely visible. Well, you've probably heard of dark matter and dark energy, and we don't really know what it is at all. So that's a shocking. If you think, say, Darwin He only knew about, I don't know, say he only knew about frogs and lizards, and he tried to develop a theory of evolution, not knowing about elephants or fish or anything like that. It'd be very hard. Well, cosmologists have developed a theory of the universe, cosmology, based on only the 5% that they've seen. And they've now discovered there's another 95%, and they've got no idea what it is.
What do you find most fascinating in your discussions with scientists?
I mean, I find most fascinating what we don't know. I think that one of the problems with often science teaching is that we kind of give people or children the impression that it's all cut and dried, that we know everything. But in fact, the most interesting thing is we don't. I think Newton said something, something like the greater the continent of knowledge, the greater the coastline of the unknown. And that's absolutely true. So what's so interesting is that we've discovered so much, but it's allowed us to pose many more questions. And as I said, what's most exciting is that these fundamental questions may have answers, certainly within maybe the next 10 or 20 years. I mean, that is absolutely incredible. I mean, if we get back to black holes, there is a supermassive black hole in the heart of every galaxy, including our galaxy. By the way, we've got a very small one, and that's a real mystery why ours is so much smaller. But it may be connected to the fact that we're having this conversation. We couldn't actually have arisen in a galaxy with a very large supermassive black hole. So these things may be esoteric, or they may seem esoteric, but actually they're connected to us being here. So there's one of these in the center of every galaxy. Now, we obviously we think that they start off small and they grow bigger, by pulling in more material, by feeding on gas, that kind of stuff. But the James Webb Space Telescope was launched probably about 2.5 years ago now, on Christmas Day, I think it was. And it's seeing very, very large supermassive black holes, maybe 1 billion times the mass of the sun, in galaxies which existed only maybe 300 or 400 million years after the Big Bang. So it's only a few percent of the age of the universe. This is making it very difficult. How could they possibly have got that big that quickly? So this is really, we're coming to a crisis point now where we don't have any idea how they could have formed that quickly. So I think that's really, really exciting. As I say, what we don't have these answers to fundamental questions like what came first, supermassive black holes or galaxies of stars? Were the supermassive black holes the seeds around which gas, which became the raw materials of stars, was gathered, or did stars with galaxies of stars form first, and maybe a star cluster at the center collapsed to form a black hole which sucked in more material? We really don't know. But the fact that they're in the center of every single galaxy, and galaxies literally make no sense without their supermassive black holes. This is one of the things I write about in my book. They are a key component, because I'll just say one last thing, and that is that they are unbelievably small compared to their parent galaxies. So if you imagine a bacterium compared to London, okay, you would expect that a bacterium would not have any control over the street plan of London, wouldn't you? I mean, it's just too small. But a supermassive black hole might be very massive, but it is, compared to its parent galaxy, is basically like a bacterium compared to London. And yet we see evidence everywhere that the supermassive black holes have had an indelible impression on their galaxies. So, for instance, in every galaxy, we see that the supermassive black hole is about 1/200th the mass of the central, what we call bulge of stars. And this shows you that they have actually controlled star formation. And they do it via these jets of material. They project their power outwards, even though they're tiny, through these amazing jets. So these jets that come out of them, which we don't understand completely at all, they push away the gas in the center of a galaxy. And that's the raw material of stars. So they can actually snuff out star formation. And that, coming back to why we're having this conversation, we have this ridiculously small supermassive black hole, which is about 1,000th the size of others. I mean, Andromeda, the nearby galaxy, which is very similar to us, has one which is 50 times bigger. But our supermassive black hole has been so feeble, it's not been able to push away the gas and snuff out star formation. And therefore, there have been multiple generations of stars. So the sun is a third generation star. And in each generation, more and more heavy elements are forged. So these are elements like calcium and carbon and all the things in your body, So we
Yeah.
could not have existed in one of these galaxies with life as we know it, with a big supermassive black hole. They must be like deserts, living, deserts.
Yeah, and life as we know it is fascinating, and it's a subject that we could talk about all day. But I think it takes a while for me to process some of this stuff. So, just on the subject of life, as a scientist yourself, what are your thoughts on extraterrestrial life in the universe?
Well, the universe is very large. It would be incredibly unlikely that we were the first. I mean, one of the you may know that Enrico Fermi, who was a very famous Italian physicist who built the first nuclear reactor on a squash court in Chicago in 1942. He was working at Los Alamos, which was the in New Mexico, which was the laboratory where they built the first atomic bomb in the 1950s. And he was sitting in the canteen with a bunch of other people, and he just put down his knife and fork and he said, "Where are they?" And everyone around the table knew exactly what he meant. He was talking about extraterrestrials. So there's a really simple argument that if there are any extraterrestrials that can travel across space, they should be here. Simply because if they were intelligent enough, they could build a probe that could replicate itself. So imagine if we had one, it went to Alpha Centauri, the nearest star system. We know there's a planet around one of the stars there, which appears in, of course, the Netflix series, The Three Body Problem. And it got there, used the raw materials to build two of itself. And then they went off to the next star systems, built four, eight. We know this is what's called exponential increase. This is how, SARS virus spread COVID, because it can spread exponentially fast. And even if the travel between stars was very slow, it's much smaller than the speed of light. You could explore every single star system, every planetary system in our galaxy in maybe 100 million years, which is a tiny fraction of the age of the universe. So that this is what Fermi was reacting to. The idea, well, if they're out there, they must be here. But of course, the thing is that absence of evidence is not evidence of absence. There's could be multiple reasons why we haven't seen any. I mean, we our surveys have tended to be of radio waves. I mean, we only invented radio communication about 1910, 1920. So we've only been using radio waves for communication for about 100 years. I mean, maybe extraterrestrial civilizations move on to something a bit more sophisticated than that. So Carl Sagan in his wonderful book, what was it called? The Cosmic Connection. He talked about tribes in New Guinea that lived in very deep valleys and were cut off from everyone else. And if you asked them, he said, how a very advanced civilization, they used a big drum, by the way, to communicate between neighbouring valleys. And he asked how would they, communicate even further away? And they would say, we use a bigger drum. And again, we would just now say use, radio waves and a bigger radio telescope. But maybe the interstellar communications are going through us all today. I mean, if you brought Isaac Newton forward, he would be amazed to realise that there's all this communication, internet traffic, and everything going through the air all around us. So yeah, I think, and the other thing is that, so I think it's really unlikely that we are the first in our galaxy. But the most likely thing is that the nearest other extraterrestrial civilization is a long way away, or we've missed it by 100 million years, 10 million years. That's the most likely thing. Or the third possibility, it isn't life as we know it. I mean, we're arguing from one example, one biology.
Yeah.
So we don't know. We think that our kind of life requires complex biological molecules, but maybe there are other forms.
Yeah, on a different plane or realm, perhaps.
Well, maybe that one of the characteristics of life is its complexity. But there might be other systems in which you can get complexity. You might get complexity in hot plasmas, or I don't know. I mean, famously, Fred Hoyle, the British cosmologist who coined the term Big Bang. Although he never believed in it, he coined the term Big Bang. He wrote a wonderful novel called The Black Cloud. which was about a cloud of hydrogen gas that came through the solar system, and it was intelligent. So who knows? Maybe there are other forms of complex organisation that don't involve biological molecules.
Yeah, the whole subject is fascinating, Marcus. If we've got any listeners that are interested in a career in astrophysics, what advice would you give them?
My advice would be to pursue it, because I mean, the temptation might be to do something that you think going to lead to a job, but you don't actually know. We're certainly living in a very uncertain world now, where we don't even know what jobs will exist in the future. So my dad's advice, which was always to do the thing that interested me, was the right advice. You do much better doing the thing that you enjoy doing. And really, physics itself is a subset of astrophysics, because obviously physics is materials that we use on Earth, but we can only use a limited range of densities, a limited range of temperatures. But of course, the universe is a much more is a much bigger laboratory, where we see matter under unbelievable extremes. We see matter at millions of degrees. We see gravitational waves. I mean, only 2015 we detected gravitational waves for the first time. These are ripples in the fabric of space, and they were produced by basically two black holes merging and 3 times the mass of the sun vanishing in an instant and reappearing as basically a tsunami of tortured space-time that spread outwards. And this object itself, this event shone. Well, the power in this event in these gravitational waves was 50 times greater than the power emitted by all the stars in the world, in the universe together. So, in other words, if it had not produced gravitational waves, but it produced optical light, it would have shone 50 times brighter than the entire universe. So again, that's showing you that these extremes exist out in space that don't. So my advice would be, do it, because if you're really interested, you're going to do much better in something that you're interested in, and it's useful physics which could be applied anywhere else as well.
Yeah, I think it's an exciting time. What are you currently working? Obviously, the book came out a couple of months ago. What are you working on now, Marcus?
I'm not really sure, but an interesting thing that's happened is that at many of the talks I've done, people have come up to me and said, you should write a book about the women scientists who've not got the credit they deserve. And the reason for that is that I write about Louise Webster, who was the co-discoverer of black holes. She was an Australian, and she's been entirely forgotten, entirely written out of the history of science. Unfortunately, she had one of the first successful liver transplants in Australia. She went back to Australia. She made her discovery at the Royal Greenwich Observatory in England, and then unfortunately she got cancer and died at 49. But she's been entirely forgotten. Oh. And of course, another person I mentioned is Jocelyn Bell, who discovered pulsars in 1967. These are neutron stars. These are stars the size of Mount Everest, which weigh as much as the sun. And again, there've been 3 Nobel Prizes for pulsars, and none have been given to her. So that's an interesting thing to think about. I'll think about that. There are quite a lot of women who've made really important contributions to science. I mean, just mention one other, and that's Emmy Noether. Have you heard of Emmy Noether?
No.
Which came up with the most important idea in the whole of physics, and it is the motivating force for fundamental physics. She discovered in 1918 that the great conservation laws of physics, the fact that energy cannot be destroyed, it can only be changed from one form into another, momentum, there's all these conservation laws, are basically nothing but manifestations of the symmetry of space. So the fact that space and time, so they're a manifestation of things that are not changed. So, for instance, if you do an experiment today and you do it tomorrow, you should expect it to get the same result. Okay, this is called time translation symmetry. And this spawns the conservation of energy. So at the Large Hadron Collider, they look for symmetries. That's what they look for. Because if they can find a symmetry, something that doesn't change, so for instance, total electric charge doesn't change. that tells them that there is a conservation law. So this is the guiding light of fundamental physics, and nobody knows the name of Emmy Noether. She was one of the most important mathematicians in history and made probably the most important contribution to physics.
Well, it sounds like there's a definite opportunity for a book there, Marcus.
We'll see. My only worry is, of course, ideally it would be written by a woman.
Yeah. You mentioned earlier on about the black holes could be seen emitting stuff.
Well, nothing can come out of a black hole. That's fundamental, right? So what we're actually seeing is material which swirls into the black hole and is projected outwards. So if you imagine the accretion disk, this million-degree disk of inswirling matter, it's kind of like an old-style CD, that kind of shape, and it gets to millions of degrees. And there are magnetic fields in this accretion disk, and material at different distances from the black hole in the accretion disk orbits at different rates. So the magnetic fields get twisted, rather like rubber bands getting twisted. And eventually, if you twist rubber bands, they snap. And this is exactly what happens. So the magnetic fields get twisted to such an extent that they snap, and somehow this projects material out along the poles of these objects. And as I say, these jets are fantastically collimated. They are thread thin, and they travel for millions of light years. And when they hit the intergalactic medium, it's rather like water from a hose hitting a brick wall. Water from a hose would splash back off the wall. And that's exactly what happens. So these oppositely directed jets, They hit the intergalactic medium, material splashes back and creates these giant radio-emitting lobes on either side of the black hole. And there is another. You may have heard of Hawking radiation. This is predicted by Stephen Hawking in the 1970s that black holes are not entirely black. They actually do emit something. And it's called Hawking radiation. This is a consequence of quantum theory. It's practically, there's no real chance we'll ever detect it. And that's probably why Hawking never got the Nobel Prize, because for normal mass black holes, it's too weak. But interestingly, it doesn't come from inside the black hole. It comes from just outside the event horizon. So, there is material that comes. So, as I say, one of the ridiculous things is the central characteristic of black holes is that stuff tends to come out, or it's the most obvious thing is that stuff is coming out.
Getting back to the book, like I said at the beginning, it's a great book. I was able to understand it clearly. What I found was that it was, when I first started reading it, I thought I'm gonna have to really research this as I read it. But what I found was the best way to approach it was just to keep reading, and those same subjects came back again in a slightly different format. And by the end of the book, my understanding had improved quite a lot. How do you go about writing a book like that, Marcus?
Yeah, well, mostly I write for my wife, who's an NHS nurse. She doesn't have any science background. Obviously, she has some medical background. So, if she gets bored and she turns up the volume on EastEnders, I have to try harder. So that's kind of my audience. My audience is really not. Obviously, I write for people who have a science background, but mostly my audience is people who don't have a science background. And I live in terror of them getting bored. I really do. So my first draft contains a vast number of exclamation marks, which of course editors tend to remove, and that's basically my desperation. So what I tried to do here is make it really immediate and tell really, hopefully, captivating stories of the people who made these discoveries. Many of whom are unknown, and make it really immediate, so that you're maybe it's almost as if you're sitting on their shoulders, standing behind them, when they make these discoveries, and intertwine, or interleave the science in this human story in hopefully a painless way. So that's what I try and do. So every chapter does begin with, a story about a person, and you're with them as they make their discoveries.
Yeah.
And early in the book, obviously, unfortunately, they're dead. Carl Schwarzschild, who first of all predicted the existence of black holes, he died in the First World War. So I had to use oral histories, but anybody who was alive, I talked to. So Roy Kerr, who basically found the first, what we call, solution of Einstein's equations for 47 years in 1963. He's a New Zealander. Basically, it's a description of the space time around a spinning black hole, a realistic black hole, he's 89, but he's very. So I managed to get hold of him, and he was very, very chatty, very controversial, in fact. So I couldn't actually include a lot of things he told me because he was quite scathing about some other people in the field. But
Right.
so I try and, if at all possible, to get their stories. So, for instance, Paul Murdin that I talked to, who co-discovered stellar black holes with Louise Webster, and he told me things like he's celebrated by buying Knickerbocker glories for his two young boys, in a beachfront cafe in Hastings. It was February, so it wasn't very nice. And to my mind, that's a wonderful story because there's a massive contrast between that. He discovers black holes and he celebrates with Knickerbocker glories, and the man who predicts them, Carl Schwarzschild, dies of a horrifying skin disease in the First World War. So, it's getting these kind of stories. I mean, basically, I interview people for several hours, and when I get off Zoom or off the phone, I've got a notebook full of things that nobody else knows because nobody's. Many of these people I talk to, no one else had talked to them, and there's loads of books about black holes. So that's real. You get a real thrill when you've learned things that no. But the other problem is that many scientists are quite careful in what they say to you, and sometimes it can be like getting blood from a stone. But Roy Kerr was definitely a very, very colourful character. It was very interesting to talk to.
Was he? Yeah. Well, the stories certainly come across through the book, and I think it helps with the understanding of the science, so I can see that. Well, Marcus, this has been a really fascinating conversation. It's been interesting to learn more about black holes. I think we've all heard of them, but many of us have limited knowledge about them, and it's good to have some more clarity and understanding. My guest today has been Marcus Chown. Marcus is an award-winning writer and broadcaster, and author of the book A Crack in Everything, How Black Holes Came In From the Cold and Took Cosmic Centre Stage. You can find links to Marcus's work and the book in the show notes. Thank you for coming on the show, Marcus.
Thank you. I really enjoyed it.